dear students, last class we discussed about heat capacity, specific heat capacity, relationship between heat capacity at constant pressure and volume, etc. Today we are going to discuss about different types of enthalpy. Okay, I'll start with enthalpy of reaction. Now, what is the enthalpy of reaction? When a reaction proceeds, that is when a reactant converts to product, when a reaction proceeds, if you consider a system having U1 internal energy and let the volume be V1. So, U1 plus PV1 is equal to H1, right? Enthalpy is the sum of internal energy and pressure volume energy. Let P be the pressure. So, enthalpy is the sum of internal energy and pressure volume energy. Let enthalpy of reactant be H1. This is the reactant. Okay. Now, this reactant is undergoing a change and converted to product. Let the internal energy of product be U2 and volume be V2. So, U2 plus PV2, internal energy pressure volume energy is H2. Let H2 be the enthalpy of product. Okay, so when a reactant converts to product, it may absorb heat energy. It may absorb heat energy at constant pressure. Okay, or it may release heat energy at constant pressure, right? At constant pressure, here pressure is constant. Always reaction proceeds at constant pressure. Okay, we discussed this topic when we discussed about enthalpies. So, we already discussed this topic. All the reaction in the universe occurs at constant pressure. So, when a reactant absorbs heat energy, or when it is released, when it releases heat energy, there it will convert to product, and there is a change in enthalpy. Enthalpy of reactants and products are not same. There will be always a difference in energy. I think it's clear. When a reactant absorb or release heat energy, that reactant will convert to product. So, enthalpy, sum of internal and pressure volume energy is known as enthalpy. Enthalpy of reactant and product are not same. There is always a change in enthalpy. So, what is enthalpy of reaction? It is the enthalpy change accompanying a reaction. So, when a reaction proceeds, there is a change in enthalpy because the reactant having U1 internal energy, H1 enthalpy absorbs or release heat energy. As a result, it will convert to product having different enthalpy, right? H2. That means here reactant, when a reactant convert to product, there is a change in enthalpy due to absorption of heat or release of heat. So, enthalpy of reaction means it is the enthalpy change. There is a change in enthalpy when a reactant is converted to product, or when a reaction occurs. It is the enthalpy change accompanying a reaction. Reaction means reactant converted to product. So, when a reactant convert to product, there is always a change in enthalpy because a reactant will convert to product only by absorbing heat energy or by releasing heat energy, so the enthalpies will change. Now, the change in enthalpy when a reaction proceeds is known as enthalpy of reaction, represented by delta HR. Now, enthalpy of reaction is calculated using this formula: enthalpy of products minus enthalpy of reactants. Let this be the enthalpy of product. This will be the enthalpy of reactant. So, enthalpy change or enthalpy of reaction is equal to enthalpy of product minus enthalpy of reactant. Okay. For example, if A moles of A react with B moles of B, giving C moles of C and D moles of D, these two are the reactants and these two are the products. Right? These two are reactants and these two are products. So, that enthalpy of product here, C and D are products, so you have to add enthalpy of product. Enthalpy of C plus enthalpy of D. This is the enthalpy of product. And here in this case, we have to add enthalpies of reactant. A and B are reactant, so we can add enthalpy of A plus enthalpy of B. So these two are reactant, right? So in this equation, we can write a sigma values or summation. The sigma indicate sum of enthalpy of products. We have to add enthalpies of each product, that is the total enthalpy of product. We have to add enthalpies of each product, that is the total enthalpy of product. Okay, minus, we have to add enthalpy of O reactant. There are two reactant, so you can write summation. Summation means addition. Addition of enthalpies of all reactant. Addition of enthalpies of all product minus addition of enthalpies of all reactants. Okay, so this is the equation to calculate enthalpy of reaction. I think it's clear. When a reactant absorbs heat energy or release heat energy, it will convert to product. Now suppose if HR, let the enthalpy of reactant be HR, H1 or HR. Enthalpy of reactant H1 or HR. Okay, let the enthalpy of product be H2 or HP. Enthalpy of product HP or H2. Now when a reactant convert to product, there is a change in enthalpy due to absorption or release of energy. So there is a change in enthalpy. There is a change in enthalpy, right? There is a change in enthalpy when a reactant convert to product. So enthalpy of reaction means it is the enthalpy change accompanying when a reactant convert to product. Reactants convert to product. Those reactions are the. So when a reactant convert to product. I think it's clear. The enthalpy change accompanying a reaction. When a reactant convert to product. That is reaction. Formula: enthalpy change of reaction. Enthalpy of reaction is equal to and the summation of enthalpy of products minus summation of enthalpy of reactant. If there are two reactants, you have to add both the enthalpies of both the reactant. Now if there are two products, we have to add enthalpies of both the product. Okay, summation indicate addition of enthalpies of a whole product. If there are two products, we have to add enthalpy of product, and if there are two reactant, we have to add enthalpy of reactant. So enthalpy of reaction is equal to summation of enthalpy of products minus enthalpy of reactant. Okay, I think it's clear. Moving on to next topic, standard enthalpy of reaction. Standard enthalpy of reaction. Now enthalpy of reaction is represented by delta HR. Standard enthalpy, for standard enthalpy, we have to write a 0 here. Standard enthalpy of reaction. Standard enthalpy of reaction. Now, what is standard enthalpy of reaction? It is the enthalpy change accompanying a reaction when all the substances are in their standard state. So, if reactants and product, when reactants convert to product, if both the reactants and products are in their standard state, if reactants and products are in their standard state, then the enthalpy change accompanying the reaction is known as standard enthalpy of reaction. When reactants and products are in their standard state, then the enthalpy change accompanying when a reactant is converted to product. It is the enthalpy change accompanying a reaction. Reaction means reactant convert to product. When all the substances are in their standard state, that means it is the enthalpy change accompanying when a reactant convert to product. And here there is one condition, that means here reactants and product are in their standard state. Okay, are in their standard state. What does mean by standard state? Standard state means pure form of a substance at 1 bar pressure and at any or at specified temperature. It is the pure form of substance at 1 bar pressure and at any specified temperature. So it is the pure form of substance. For example, if reactant is at 1 bar pressure and if reactant is pure, same way, if product is at 1 bar pressure and if it is pure, then this condition is known as standard state. Okay, so when reactants and products are in their standard state, that is pressure 1 bar and reactant should be pure. Product 1 bar pressure and product should be pure. If reaction and products are in their standard state, then enthalpy change accompanying at that time is known as standard enthalpy of reaction, delta HR0. It is the enthalpy change accompanying a reaction, that is reactant convert to product is known as reaction. A reaction when reactants and products are in their standard state. Standard state means if if a substance, it's a pure form of a substance, standard state means pure form of a substance at 1 bar pressure and at any specified temperature, Okay, two important conditions are pure form and 1 bar pressure. If reactants and products are pure and their pressures are 1 bar, then we can consider reactants and product as standard state. Enthalpy change accompanying, that is, if the enthalpy of reactant is HR, and if enthalpy of products are HP, reactant will convert to product by absorbing heat energy or by releasing heat energy, right? So enthalpy change, there is a change in enthalpy of reactant HR and enthalpy of product HP. So there is a change in enthalpy, but here reactants and products are in their standard state. So this enthalpy change is known as standard enthalpy of reaction. I think it's clear. Moving on to next topic, values of delta HR. So values of enthalpy of reaction, delta HR. Delta HR possesses two values. Delta HR can have negative value and delta HR can have positive value. Okay. Now, for exothermic reaction, delta HR value is negative. What does mean by exothermic reaction? When a reactant convert to product by releasing heat energy, when a reactant convert to product by releasing heat energy at constant pressure, then those processes are known as exothermic process in which heat energy is released. So when a reactant convert to product, if heat energy is released, those processes are known as exothermic reaction. Let enthalpy of reactant be HR and enthalpy of product be HP. Now we know that when reactant convert to product by releasing heat energy, this indicates that enthalpy of reactant is greater than product, because this reactant is liberating heat energy, so that energy of product will be less. Here reactant is liberating heat energy, so energy of product will be less, that is enthalpy of product will be less, right? So here in the case of exothermic reaction, that is reaction where heat is released, here enthalpy of reactant is greater than product. So what is delta HR? Enthalpy of reaction is equal to enthalpy of products minus enthalpy of reactant. Here enthalpy of product is less and here enthalpy of reactants are more, right? Enthalpy of product is less compared to enthalpy of reactant. So what is HP minus HR? You will get a negative value because enthalpy of reactant is more. So lower value minus higher value, you will get a negative value. For exothermic reaction, delta H value is negative. I think it's clear. So what exothermic process? Process in which a reactant convert to product by liberating heat energy. Now for exothermic reaction, enthalpy of reactant is greater than product, because here in exothermic reaction heat energy is liberated when a reactant convert to product. That indicates that energy of reactant is greater than product, but because here energy is liberated and after liberating heat energy it is converted to product, so that energy of product will be less. So HP minus HR will be a negative value. So for exothermic reaction, delta H value will be negative. Now in the case of endothermic process, what do I mean by endothermic process? Endothermic process means when a reactant convert to product by absorbing heat energy. Reactant convert to product by absorbing heat energy at constant pressure. Those processes are known as endothermic process. Okay, reactants are converted to product by absorbing heat energy. Those processes are known as endothermic process. Now, in the case of endothermic process, enthalpy of reactant is less, whereas enthalpy of products. Okay, so enthalpy of products is greater than enthalpy of reactant, because here reactant absorbs heat energy and convert to product. That means after absorbing heat energy, reactants are converted to product. That indicate energy of product is greater than reactant, or enthalpy of product is greater than reactant. So delta HR is equal to summation of HP minus HR. Here enthalpy of product is greater than enthalpy of reactant. Obviously you will get delta H value positive. So for endothermic reaction, delta HR value equal to positive. So enthalpy of reaction, delta HR possesses two values, negative and positive. For exothermic reaction, enthalpy of reaction, delta HR is equal to negative. At the same time, for endothermic, delta HR is equal to positive. Exothermic, delta HR negative, endothermic, delta HR positive. I think it's clear. Moving on to next topic. Types of enthalpy of reaction. Now, enthalpy of reactions are classified into different category. Enthalpy of reaction, delta HR. Enthalpy of reactions are classified into different category. Okay. First one is enthalpy of formation represented by delta HF. First one, enthalpy of formation. Okay. Types of enthalpy of reaction. Enthalpy of reactions are classified into different types. First one is enthalpy of formation represented by delta HF. Second one, enthalpy of combustion represented by delta HC. Enthalpy of combustion. Third one, enthalpy of atomization represented by delta HA. Okay. Now, next one, enthalpy of solution. Enthalpy of solution represented by delta H SOL. Solution. Delta H SOL. Solution. Now, next one, enthalpy of phase transition. Enthalpy of phase transition is again classified into three types. Enthalpy of phase transition. So first one, enthalpy of formation represented by delta HF. Second one, enthalpy of combustion represented by delta HC. Third one, enthalpy of atomization represented by delta HA. Now fourth one, enthalpy of solution represented by delta HSOL. Solution. And fifth one, enthalpy of phase transition. Now enthalpy of phase transitions are again classified into three types. Enthalpy of fusion represented by delta H FUS, fusion. Second one, enthalpy of vaporization represented by delta H VAP. Next one, enthalpy of sublimation represented by delta H SUB. Okay, so enthalpy of phase transition again classified into three types. Enthalpy of fusion, delta H FUS. Enthalpy of vaporization, delta H VAP. Enthalpy of sublimation, delta H SUB. And last one, bond enthalpy. Last one, bond enthalpy represented by delta H bond. Delta H bond. So enthalpy of reaction, it is again classified into different category. First one, enthalpy of formation, delta HF. Second one, enthalpy of combustion, delta HC. Third one, enthalpy of atomization, delta HA. Fourth one, enthalpy of solution, delta H SOL. Fifth one, bond enthalpy, delta H bond. And last one, enthalpy of phase transition. Now this enthalpy of phase transition are of three types. Enthalpy of fusion represented by delta H FUS. Second one, enthalpy of vaporization, delta H VAP. And third one, enthalpy of sublimation represented by delta H SUB. So we are going to study each and every topics in detail. Okay. So moving on to first one, enthalpy of formation. Now what is enthalpy of formation? It is the enthalpy change accompanying when 1 mole of a compound is formed from its constituent elements. It is the enthalpy change accompanying when 1 mole of a compound is formed from its constituent element. That means when two or more elements combines to form a compound, 1 mole of a compound, the enthalpy change accompanying in that reaction is known as enthalpy of reaction. For example, consider Consider this reaction. Carbon solid react with oxygen gas to produce carbon dioxide. Okay, now if you consider this reaction, here 1 mole of carbon dioxide is produced from carbon element and oxygen element. So here 1 mole carbon dioxide is produced from carbon element and oxygen element. So enthalpy of formation means it is the enthalpy change accompanying when 1 mole of a compound is formed from its constituent elements. So 1 mole of a compound is formed from its constituent element. So at that time that enthalpy is known as enthalpy of formation. Okay, I think it's clear, enthalpy of formation. When we consider second example, CO plus half O2 giving 1 CO2. Now, if you consider this reaction, now this reaction is not an example for enthalpy of formation. This reaction is not an example for enthalpy of formation because here 1 mole of compound is produced. Yeah, that's okay. 1 mole of compound is produced. But what is enthalpy of formation? 1 mole of compound is formed from its constituent elements. Here 1 mole of compound is produced, but it is not produced from constituent element because this one is element, but this is not element, this is a compound. This one is a compound, it's not an element. What is enthalpy of formation? It is the enthalpy change. It is the enthalpy change accompanying occurs when 1 mole of a compound is formed from its constituent element. Here 1 mole of compound is formed, but here it is not formed from corresponding elements. This one is compound, but oxygen is element. Okay, now if you consider this reaction, 2 Mg plus O2 gas solid giving 2 MgO. Now if you consider this one, magnesium oxide. Now if you consider this one, okay, here 2 elements combines to form a compound, but this reaction is also, it is not considered as enthalpy of formation. Okay, or this reaction is not considered as formation reaction. Why this is not considered as formation reaction? Here elements combines to form how many moles of product? 2 moles. What is enthalpy of formation? What is formation reaction? What is formation reaction? 1 mole of compound is formed from its constituent element. That is formation reaction, and enthalpy change accompanying that reaction is known as enthalpy of formation. Here we are not producing 1 mole, we are producing 2 mole. So this reaction is not an example for enthalpy of formation. So what is enthalpy of formation? What is formation reaction? Formation reaction means 1 mole of compound. 1 mole of compound is produced from constituent elements. Those reactions are known as formation reaction, and enthalpy change occurring. Always when a reactant convert to product, there is a change in enthalpy, and that enthalpy change is known as enthalpy of formation, represented by delta HF. Delta HF. I think it's clear. Now, standard enthalpy of formation. Now what is standard enthalpy of formation? If the same reaction occurs, it is the enthalpy change accompanying when 1 mole of a compound is formed from constant element at standard state. When 1 mole of a compound is formed from constituent element at standard state. The same reaction, if the same reaction occurs under standard state. What is standard state? We have already discussed standard state. What is standard state? Standard state means pure form of a compound at 1 bar pressure and any specified temperature. These are the 2 important conditions. Pure form at 1 bar. This is the 2 important condition that is known as standard state. Now if reaction occurs under standard condition, then that enthalpy of formation is known as standard enthalpy of formation, represented by delta HF0, 0. Okay, I think it's clear. So what is formation reaction? Formation reaction means 1 mole of compound is formed from its constituent element. 1 mole of compound is formed from its constituent element. Those reactions are known as formation reaction, and enthalpy change accompanying those reactions are known as enthalpy of formation. Now, if that reaction proceeds under standard condition, that is pure form, 1 bar pressure, then that enthalpy of formation is known as standard enthalpy of formation, represented by delta HF 0, or you can use theta. This is theta, or you can use theta or 0. You can use anything, theta or 0. Okay, this is enthalpy of formation or standard enthalpy of formation. I think it's clear. Moving on to next enthalpy. Moving on to second enthalpy, that is enthalpy of combustion. Now, what is enthalpy of combustion? It is the enthalpy change occurring when 1 mole of a substance react with excess of air or oxygen. So it is the enthalpy change occurring when 1 mole of a substance react with air or oxygen. Example: if carbon solid react with oxygen to produce carbon dioxide, okay, you can consider this reaction as enthalpy of combustion, or this reaction is known as combustion reaction. This reaction is combustion reaction. Why this reaction is considered as combustion reaction? What is combustion reaction? 1 mole of a substance react with excess of air or oxygen. Those reactions are known as combustion. Here we are taking 1 mole of carbon element. So here carbon element, 1 mole carbon element react with, you can use excess of oxygen. Here amount of oxygen is not important. Here amount of carbon is important. So 1 mole carbon, 1 mole substance. So carbon is an element. Okay. So you can consider element as substance. So 1 mole substance react with excess of air or oxygen to form carbon dioxide. You can consider this reaction as a combustion reaction. Okay. So enthalpy change accompanying this reaction is known as enthalpy of combustion, represented by delta HC. Now, this one is an example for both enthalpy of combustion and enthalpy of formation, because here 1 mole product is formed from constituent element. 1 mole compound is formed from this constituent element. So you can consider this reaction as formation reaction, or you can consider this reaction as combustion reaction. Okay, I think it's clear. So this reaction is an example for both formation reaction, because 1 mole of compound is formed from its constituent element, or combustion reaction because 1 mole substance react with excess of air or oxygen to form corresponding product. So this one is example for combustion reaction and formation reaction. Okay, now next one, example 2. CO react with half O2 gas giving CO2 gas. Now if you consider this reaction, this one is an example for combustion reaction because we are using 1 mole of compound. So here 1 mole of compound react with excess of air or oxygen to form carbon dioxide. 1 mole compound react with excess of air or oxygen to form carbon dioxide. So this one is an example for combustion reaction. So enthalpy change accompanying this reaction is known as enthalpy of combustion. Okay, so we can use element as well as compound, but the important condition is if we are using elements or compound, the number of moles should be 1. Generally elements or compounds are known as substance. Okay, generally elements and compounds, they are generally known as substance. So it is the enthalpy change accompanying when 1 mole of substance, it can be element or compound, react with excess of oxygen. Amount of oxygen is not important here, okay, to produce corresponding product. This reaction is known as combustion reaction, and enthalpy change is known as enthalpy of combustion, represented by delta Hc. Okay, now standard enthalpy of combustion. Now what is standard enthalpy of combustion? It is the enthalpy change accompanying when 1 mole of substance react with excess of air or oxygen. Okay, at standard state. It is the enthalpy change accompanying when 1 mole of a substance react with excess of air or oxygen at standard state. It is the enthalpy change accompanying when 1 mole of a substance react with excess of air or oxygen. Okay, at standard state is known as standard enthalpy of combustion. So I think we have discussed two important reactions. First one is formation reaction. What is formation reaction? When 1 mole of a compound is formed from its constituent element, those reactions are known as formation reaction, and enthalpy change accompanying those reactions are known as enthalpy of formation. Now second reaction, enthalpy of combustion. It is the enthalpy change accompanying when 1 mole of a substance, here substance means it can be element or compound. So 1 mole of element or compound, generally substance, react with excess of air or oxygen to at standard condition, air or oxygen is known as enthalpy of combustion. And if the reaction occurs under standard state means pure form 1 bar, then that enthalpy of combustion is known as standard enthalpy of combustion, represented by delta Hc theta or 0 theta. Okay, I think it's clear. Moving on to third enthalpy, that is enthalpy of atomization. Now what is enthalpy of atomization? Before that, what is atomization reaction? Atomization reaction means 1 mole of compound dissociate to form corresponding elements in gaseous state. This reaction is known as atomization reaction. 1 mole of compound dissociate to form corresponding elements in gaseous state. For example, if you consider methane, and this 1 molecule methane, 1 mole of a compound, so 1 mole methane dissociate to form carbon and hydrogen in gaseous state. 1 mole of compound, 1 mole of methane. I'm taking 1 mole of methane, and this 1 mole of methane dissociate to form corresponding elements. When this molecule dissociate, it will produce carbon and hydrogen, corresponding elements in gaseous state. Then those reactions are known as atomization reaction. It is the enthalpy change accompanying. And okay, what is atomization reaction? When 1 mole of compound dissociate to form corresponding elements in gaseous state, those reactions are known as atomization reaction, and enthalpy change accompanying those reactions are known as enthalpy of atomization. It's known as enthalpy of atomization, represented by delta HA. It is the enthalpy change accompanying when 1 mole of compound dissociate to form corresponding elements in gaseous state. Okay, this is known as enthalpy of atomization. I think it's clear. Now what is standard enthalpy of atomization? Standard enthalpy of atomization. It is the enthalpy change accompanying when 1 mole of compound dissociate to form corresponding elements in gaseous state under standard condition. Under standard condition or under standard state, represented by delta HA theta. Okay, so if atomization reaction occurs under standard condition, then the enthalpy change is known as standard enthalpy of atomization. I think it's clear till here. So it is the enthalpy change accompanying when 1 mole of a compound dissociate to form corresponding elements in gaseous state. Okay, that is enthalpy of atomization, and if this reaction occurs under standard condition, then that is known as standard enthalpy of atomization, represented by delta HA theta. Okay, moving on to fourth one, that is enthalpy of phase transition. Enthalpy of phase transition. Now what is mean by phase transition? Phase transition means if a solid is converting to, or when a solid melts to liquid, okay, we can say that this is a phase transition reaction. When a solid converts or melts to liquid, then we can say that that reaction is a phase transition reaction, because solid is converted to liquid. There is a change in phase. Now if liquid is converted to gas, we can say that that reaction is also a phase transition reaction. So solid converts to liquid is an example for phase transition reaction. Liquid convert to gas is an example for phase transition reaction. Gas convert to solid is another example for phase transition reaction. Okay, so phase change reaction in which there is a change in phase. Okay, so enthalpy of phase transition. Now phase transition reactions are classified into 3 types: fusion reaction, vaporization reaction, and sublimation reaction. I'll start with fusion reaction. So first one, enthalpy of fusion. First one, what is fusion reaction? What is fusion reaction? What is fusion reaction? Fusion means conversion of solid to liquid. 1 mole solid melts to liquid. Solid to liquid. Solid melts to liquid. This reaction is known as fusion. Solid melts to liquid is known as fusion reaction. Now, if 1 mole of solid melts to liquid, there is a change in enthalpy. That enthalpy change is known as enthalpy of fusion, delta HFUS. So it is the enthalpy change. It is the enthalpy change. There is a change. When a solid converts to liquid, there is a change in enthalpy. Always when a reactant convert to product, there is always a change in enthalpy. So in enthalpy of fusion, there is a change in enthalpy. There is a change in enthalpy accompanies when 1 mole of solid convert to liquid. It is the enthalpy change accompanying when 1 mole of solid convert or melt to liquid. And solid will melt to liquid at its melting point. So it is the enthalpy change accompanying when 1 mole of solid melts to liquid at its melting point. Always solid melts to liquid at its melting point. So I think it's clear. So enthalpy of phase transition. Enthalpy of phase transitions are again classified into 3 types. Enthalpy of fusion, enthalpy of vaporization, enthalpy of sublimation. One among them is, first one is enthalpy of fusion, represented by delta H FUS. Now what is fusion reaction? If 1 mole of solid melts to liquid, then that reaction is known as fusion reaction. Enthalpy change accompanying during fusion reactions are known as enthalpy of fusion, represented by delta H FUS. And usually fusion reaction always occur at melting point, at its melting point. So it is enthalpy change accompanying when 1 mole of solid melts to liquid at its melting point. Now, what is standard enthalpy of fusion? What is standard enthalpy of fusion? What is standard enthalpy of fusion? Standard enthalpy of fusion represented by theta. It is the enthalpy change accompanying when 1 mole of solid melts to liquid at standard state. So standard state. It is the enthalpy change accompanying when 1 mole of solid melts to liquid at standard state. What is standard state? What is standard state? Standard state means pure form at 1 bar, pure form of a substance at 1 bar pressure. This is the standard state condition. So I think it's clear. So standard enthalpy of fusion means it is the enthalpy change accompanying when 1 mole of solid melts to liquid at standard state. Okay. Now, what is enthalpy of fusion? It is the enthalpy change accompanying when 1 mole of solid melts to liquid at its melting point. Okay. If it is simply enthalpy of fusion, you have to write at its melting point. If it is standard enthalpy of fusion, then instead of at its melting point, you can add standard state. I think it's clear. Moving on to second one. Second phase transition reaction, that is vaporization reaction. What is vaporization reaction? It is vaporization reaction means 1 mole of liquid vaporize. Liquid to gas. That reaction is known as vaporization reaction. Vaporization reaction. Solid to liquid fusion reaction, and liquid to vapor. That reaction is known as vaporization reaction. So what is enthalpy of vaporization? It is the enthalpy change accompanying when 1 mole of liquid vaporize. That is, 1 mole of liquid changes to gas. Water, 1 mole of liquid changes to gas. It is the enthalpy change accompanying when 1 mole of liquid vaporize. Vaporize means conversion of liquid to gas. And usually vaporization occurs at boiling point. Fusion, melting point, and vaporization usually occurs at its boiling point. So vaporization reaction means conversion of liquid to gas is known as vaporization reaction. Now what is enthalpy of vaporization? It is the enthalpy change accompanying. There is enthalpy change accompanying when 1 mole of a liquid vaporize at its boiling point. 1 mole of liquid 1 mole of liquid vaporize, that is 1 mole of liquid convert to gas. It is represented by delta H VAP, vaporization. Delta H VAP, vaporization. I think it's clear. Now, next one is standard enthalpy of vaporization. What is standard enthalpy of vaporization? It is the enthalpy change accompanying when 1 mole of liquid vaporize at standard state. At standard state. It is the enthalpy change accompanying when 1 mole of liquid vaporize at standard state. That is pure form of substance at 1 bar pressure at any specified temperature. I think it's clear. Moving on to last phase transition reaction, that is sublimation reaction. Moving on to last one. Moving on to last phase transition reaction, that is sublimation reaction. What is sublimation reaction? Conversion of solid to gas. Conversion of solid to gas is known as sublimation reaction. Sublimation reaction. Conversion of solid to liquid, fusion. Conversion to liquid to gas, vaporization. Conversion of solid to gas, sublimation reaction. Now, what is enthalpy? What is enthalpy of sublimation? It is the enthalpy change accompanying when 1 mole of solid sublimes. Sublimes means conversion of solid to gas. So when 1 mole of solid sublimes to gas, then at that time the enthalpy change is known as enthalpy of sublimation. It is the enthalpy change accompanying when 1 mole of, it is the enthalpy change accompanying when 1 mole of solid sublimates, okay, to gas, and usually sublimation take place below melting point. At melting point, solid convert to liquid. So sublimation usually take place below, that is before. If you consider this one, this is gas and this one is solid and this one is liquid. Now at melting point, solid convert to liquid. At melting point, let this be the melting point. At melting point, solid convert to liquid. Now solid convert to gas below melting point. If solid reach melting point, it will convert to liquid. So before that we have to convert to gas, right? So usually solid will convert to gas below its melting point. When a solid reach its melting point, it will convert to liquid. So before that we have to convert to gas. So it is the enthalpy change accompanying when 1 mole of solid sublimates below its melting point. 1 mole of solid converted to gas below its melting point. It is represented by delta H SUB, sublimates. Delta H SUB, enthalpy of sublimation. Now what is standard enthalpy of sublimation? It is the enthalpy change accompanying when 1 mole of solid sublimates at standard state, represented by delta H SUB theta, delta H SUB theta. So if the same reaction occurs under standard condition, then that is known as standard enthalpy of sublimation. I think it's clear. Okay. So this is third one. This one is third. So phase transition reactions are of three types: solid to liquid fusion reaction, liquid to gas vaporization reaction, and solid to gas sublimation reaction. Enthalpy during fusion reaction is known as enthalpy of fusion. Enthalpy change during vaporization reaction is known as enthalpy of vaporization, and enthalpy change during sublimation reaction is known as enthalpy of sublimation. I think it's clear. Moving on to next one. Moving on to next enthalpy, that is enthalpy of solution. Moving on to next enthalpy, that is bond enthalpy or bond dissociation enthalpy. Moving on to next enthalpy, that is bond enthalpy or bond dissociation enthalpy, represented by delta H bond. Now, what is bond enthalpy? Bond enthalpy means it is the energy required to dissociate 1 mole of covalent bond in gaseous diatomic molecule. It is the energy required to break down, or it is the energy required to dissociate 1 mole of covalent bond in gaseous diatomic molecule. Consider 1 mole of chlorine atom. Consider 1 mole of chlorine. Now, chlorine usually exists in gaseous state, and this is a diatomic molecule. 2-atom molecule which contain 2 atoms, that is gaseous diatomic molecule. So consider 1 mole of gaseous diatomic molecule. 1 mole of gaseous diatomic molecule. 1 mole of gaseous diatomic molecule which consists of 2 diatomic molecule. Now, in 1 mole of, in 1 Cl, in just 1 chlorine, if you consider 1 chlorine contain 1 covalent bond. So 1 mole of chlorine, Cl2, 1 chlorine, 1 Cl2 contain 1 covalent bond. So 1 mole of Cl2 contain 1 mole of covalent bond, right? 1 Cl2, if you consider just one Cl2 molecule, if you consider just one Cl2 molecule contain 1 covalent bond, right? Then if you consider 1 mole Cl2, this 1 mole Cl2 contain 1 mole covalent bond. So energy required, it is the energy required to break down, it is the energy required to break down 1 mole of covalent bond in gaseous diatomic molecule. This energy is known as bond enthalpy or bond dissociation enthalpy. I think it's clear. So if you consider 1 mole gaseous diatomic molecule, just consider 1 molecule, 1 Cl2 molecule. First consider 1 Cl2 molecule. If you consider 1 Cl2 molecule, you can write like this: Cl single bond Cl. So 1 Cl2 molecule contain 1 bond. Then 1 mole Cl2, 1 mole gaseous diatomic. Cl2 is gaseous diatomic. So if you consider 1 mole diatomic molecule, 1 mole diatomic molecule in gaseous state, it contain 1 mole covalent bond, right? Energy required to break down 1 mole covalent bond in gaseous diatomic molecule. That energy is known as bond dissociation enthalpy or bond enthalpy, represented by delta H bond. Okay, delta H bond. I think it's clear. Now, if AA plus B, for example, if you consider AA plus BB giving AB, 2AB. So A react with B to form AB, second A molecule react to form AB, so we'll get 2AB. These two are reactants and this one is product. AB is product. So A molecule react with B, that is B molecule giving AB, 2AB. Now let the energy needed or bond enthalpy or bond dissociation enthalpy of AA bond B, let it be delta H1, let it be H1, enthalpy 1. Now bond enthalpy or bond dissociation enthalpy of BB bond B, H2. Okay, now bond enthalpy of AB bond B, H3. Okay, H3. Now from bond, if you know bond dissociation enthalpy of reactants and product, if we are aware of bond dissociation enthalpies of reactants and product, you can calculate enthalpy of reaction from these bond dissociation enthalpy value. If you know bond dissociation enthalpy, let it be H1 bond, let it be H2 bond, let it be H3 bond. If you know bond dissociation enthalpy of reactants and product, you can calculate enthalpy of reaction from bond dissociation enthalpy. Now, equation to calculate enthalpy of reaction from bond dissociation enthalpy is summation of enthalpy of reactant minus summation of enthalpy of product. Delta H summation of, that means you have to add enthalpy of reactant. Sorry, once more. If you want to calculate enthalpy of reaction from bond dissociation enthalpy, the equation is enthalpy of reaction is equal to bond enthalpy of reactant, H bond R, bond enthalpy of reactant minus bond R reactant minus bond enthalpy of products. This is the equation to calculate enthalpy of reaction. If you consider this reaction, if you want to find enthalpy of reaction, from bond enthalpies you can calculate enthalpy of reaction. Equation is enthalpy of reaction is equal to bond enthalpy of reactant minus bond enthalpy of product. This equation is used to calculate enthalpy of reaction if you know, if you are aware of bond enthalpies of reactants and product. If you know bond enthalpies of reactant and product, you can calculate enthalpy of the reaction. You can calculate enthalpy of the reaction. Okay, this is the equation. What is enthalpy of the, what do you mean by enthalpy of reaction? It is the enthalpy change occurring when reactants converted to product. So from bond dissociation value or bond enthalpies of reactant and product, you can calculate enthalpy of reaction. So once more, what is bond enthalpy or bond dissociation enthalpy? It is the energy required to break down 1 mole of covalent bond in gaseous diatomic molecule. That is bond dissociation enthalpy or bond enthalpy. Now, from bond enthalpy values of reactants and product, we can calculate enthalpy of reaction. This is the equation to calculate enthalpy of reaction from bond enthalpy of reactants and product. Delta HR is equal to summation of enthalpy of bond enthalpies of reactant minus bond enthalpies of reactant minus summation of bond enthalpy of product. Okay, here you can see two product, 2AB. AB, 2 product. That's why we have to add bond enthalpy of both the product. I think it's clear. Now, here we have to discuss one more topic. Under this heading, we have to discuss one more topic. So, moving on to next one, that is for diatomic molecule, we use bond enthalpy or bond dissociation enthalpy. For polyatomic molecule, instead of bond enthalpy or bond dissociation enthalpy, we use the term average bond enthalpy or mean bond enthalpy Okay, so for polyatomic molecule, instead of bond enthalpy, we use another term, mean bond enthalpy. Why we are using this term, mean bond enthalpy, for polyatomic molecule? We can consider polyatomic molecule. Let's consider water molecule. Consider water vapor. H2O. Now, energy required to break, just neglect this hydrogen. First, please neglect this hydrogen. First, we have to observe these two atoms, oxygen and hydrogen. Now, energy required to break down these two energy required to break down the bond between these two atoms. Let it be bond enthalpy 1. Now, this is OH bond and energy required to break down this bond. Let it be delta bond H1. Now, after breaking this bond, we will get OH plus H, right? Delta bond H1. Now, energy required to break this bond, that is this OH bond, OH and OH, there are two OH bond. Energy required to break down one OH bond is delta bond H1, and energy required to break the second OH bond, okay, is delta bond H2. Now, both the bonds are OH bond, but here the bond enthalpy for breaking two OH bonds are different because initially there are two OH bonds. So energy required to break first OH bond, okay, let it be delta bond H1. Now, after breaking this bond, now the molecule is having only one OH. Before breaking this bond, the molecule is having two OH bond. Okay, after breaking this bond, now the molecule is having only one OH bond, so that the energy will be different. Initially there are two OH bonds, so values bond delta H bond 1. But after breaking this bond, we have only two atoms, right? There is only one bond. So this bond will be different. Always, if you consider any other molecule, for example, if you consider methane. Now methane contain 4 CH bonds, right? 4 CH bonds. Now, we may think that all the 4 CH bond possess same bond enthalpy, but actually all the CH bond possess different bond enthalpy, because initially there are 4 bonds. If I'm going to break this bond, let the bond dissociation enthalpy be delta H bond 1. Now after breaking this bond, now the molecule is having only 3 bonds, so the energy will vary. Now bond energy required to break this bond be delta H2. After breaking this bond, now the compound is having only 2 bonds, so energy required to break third bond, let it be delta H3. Now after breaking this compound, now there is only 1 bond remaining, so the energy will vary. So if the energy required to break this bond, let it be delta bond H4. So here we have 4 CH bond, but actually energy required to break all the CH bonds are different. I think it's clear. So in the case of water is a polyatomic, consists of 3 atoms. Water is a polyatomic molecule. So energy required to break down 2 OH bonds will be different. Energy required to break down 2 OH bonds, it will be different. So bond. So average or mean bond enthalpy, delta H is equal to delta bond H1 plus delta bond H2 by 2. Delta bond H1 plus delta bond H2 by 2. This is the mean bond enthalpy. Mean bond enthalpy. I think it's clear. In the case of CH4, how many CH bonds are there? 4 CH bond. All the bond possess different values. So mean bond enthalpy is equal to delta H bond 1 plus delta H bond 2 plus delta H bond 3 plus delta H bond 4 divided by 4. There are 4 bonds. This is the average or mean bond enthalpy. So in the case of diatomic molecule, we are using the term bond enthalpy or bond dissociation enthalpy. But for polyatomic molecule, instead of bond enthalpy, we will use the term mean bond enthalpy, because in the case of polyatomic molecule, we can observe more than 1 bond. So for example, water, we can observe 2 bonds. Energy required to break down 2 OH bond will be different. So we have to take the average of 2 bond dissociation enthalpies, right? So for polyatomic, we use, instead of bond enthalpy, we use mean bond enthalpy. Moving on to 6th one, enthalpy of solution, represented by delta HSOL, enthalpy of solution. Now what is enthalpy of solution? It is the enthalpy change accompanying when 1 mole of solute dissolved in suitable amount of solvent to make solution. It is the enthalpy change when 1 mole of solute dissolved in suitable amount of solvent to make a solution. Okay, let us consider one example. Consider 1 mole of NaCl dissolved in water. Let's consider 1 mole of solute. 1 mole of NaCl, let NaCl be the solute. Consider 1 mole of NaCl solute dissolved in water. Let water be the solvent. Okay. Now when you add NaCl to water, let this be the water. When you add NaCl to water, first step, this NaCl, when you add NaCl to water, this NaCl first split to form Na plus gas and Cl minus gas. So when we add NaCl solute to water solvent, this first step is that this NaCl solid will split to form Na plus and Cl minus gas. The energy required for their decomposition, the energy required to split NaCl solid to Na plus gas and Cl minus gas is known as lattice enthalpy. The energy required to break down a solid NaCl to Na plus gas and Cl minus is known as lattice enthalpy, L-A-T-T-I-C-E, lattice delta H. Lattice, delta H lattice. This is known as lattice enthalpy, and here lattice enthalpy value is positive because energy is absorbed. Always absorption energy is positive. When energy is released, then that becomes negative. Here lattice enthalpy means it is the What is lattice enthalpy? Lattice enthalpy means represented by delta H lattice. It is the enthalpy change okay, is the enthalpy change, or it is the energy required, it is the energy required to break down 1 mole of solid ionic compounds to gaseous ions. Lattice enthalpy means it is the energy required to break down 1 mole of solid ionic compound. NaCl is an ionic compound. You know that NaCl. In NaCl, force of attraction between NaCl and Cl is ionic bond. So NaCl is an ionic compound. It is an ionic compound. Force of attraction between Na and Cl is ionic bond or electrostatic force of attraction. Okay. So NaCl is an ionic compound. So energy required to break down 1 mole of solid ionic compound to gaseous ion, that energy is known as lattice enthalpy. Okay, so when we add NaCl to water, okay, NaCl first split to form Na plus and Cl minus gas. NaCl solid first split to form Na plus gas and Cl minus gas. The energy required for this breakdown is known as lattice enthalpy. The energy required for this dissociation is known as lattice enthalpy. What is lattice enthalpy? It is defined like this. It is the energy required to break down 1 mole of solid ionic compound to corresponding gaseous ions. I think it's clear. Now here now this NaCl exists as Na plus and Cl minus. In water, NaCl break down to form Na plus and Cl minus in gaseous state. Step 2. This Na plus is surrounded by water molecule. This is positive charge. Now water, when we consider water, oxygen is having negative charges and hydrogens are having positive charge. Oxygen negative, hydrogens positive. So this oxygen part of water will surround this sodium ion. Okay. In a similar way, Cl minus is surrounded by H part of water. Na plus what? Positive part surrounded by Na plus is surrounded by oxygen part of water, O minus part of water. At the same time, Cl minus is surrounded by hydrogen part of water. I think it's clear. This process is known as hydration. So, this process, Na plus, ions are surrounded by water molecule, and that process is known as hydration. So hydration, due to hydration, energy is released. When an ion is hydrated by water molecule or surrounded by water molecule, energy is released. That energy is known as hydration enthalpy. H-Y-D-R-A-T-I-N, hydration enthalpy. Hydration enthalpy is negative. So what is enthalpy of solution? It is the enthalpy change accompanying when 1 mole of solute is dissolved in suitable amount of water. So when we dissolve 1 mole of solute in suitable amount of water, there is a change in enthalpy. Okay, there is a change in enthalpy. So enthalpy change associated when 1 mole of solute dissolved in suitable amount of solvent to make solution. That enthalpy is known as enthalpy of solution. Now, if we add 1 mole of NaCl solute in solvent water or water solvent, okay, this NaCl first split to form Na plus gas and Cl minus gas. Energy required for that process is known as lattice enthalpy. So lattice enthalpy is positive because energy is absorbed to break down solid ionic compound to corresponding gaseous ion. Okay, that energy is known as lattice enthalpy. It is the energy required to break down 1 mole of solid ionic compound to corresponding gaseous ion. Now, after splitting, this Na plus and Cl minus which exist in water are surrounded by water molecule, and that process is known as hydration. Now, due to hydration, energy is released. That energy is known as hydration enthalpy. Okay. Now, enthalpy of solution is the sum of lattice enthalpy and hydration enthalpy. Enthalpy of solution, delta H SOL is equal to sum of lattice enthalpy plus hydration enthalpy, because by or due to these two processes, NaCl dissolved in water. Due to these two processes, first step NaCl split to form Na plus and Cl minus, second step Na plus and Cl minus are surrounded by water molecule. This is known as solution. This is NaCl solution. Okay, so here NaCl is dissolved in water. NaCl dissolved in water to make NaCl solution. This is solution, NaCl solution. So here, when we add NaCl to water, due to these two steps, a solution is formed. So enthalpy of solution is equal to sum of lattice enthalpy and hydration enthalpy. It is the sum of lattice enthalpy and hydration enthalpy. Enthalpy of solution is equal to sum of lattice enthalpy and hydration enthalpy. I think it's clear. Moving on to next topic, Hess's law. Now, Hess's law. What is Hess's law? Hess's law states that total enthalpy change is same whether the reaction take place in a single step or several steps. Total enthalpy change is same whether the reaction take place in a single step or several steps. Consider a reaction where reactant R is converted to product P. Here, the enthalpy of this reaction be delta HR. Here, reactant R is converted to product P directly in a single step. Here, reactant R is converted to product P directly in a single step. Let the enthalpy change be delta HR. Okay. Now, consider another reaction where reactant R first converted to an intermediate A. This intermediate A then converted to intermediate B. Then this intermediate B then converted to product P. Let the enthalpy change for the conversion of R to intermediate A be delta H1. Let the second conversion, that is intermediate A to intermediate B, delta H2. Let the third step, delta B to product, intermediate B to product, let that enthalpy change be H3. Now, Hess's law states that total enthalpy change is same whether the reaction take place in a single step. Here, reactant is converted to product directly, or if it take place several steps. Here, reactant is converted to intermediate A. Intermediate A changes to intermediate B. Then intermediate B changes to product P. Here, the reaction take place in several steps. Okay. If a reaction take place in single step or several step, okay, total enthalpy change is always same. Okay, that means delta HR enthalpy change in a single step is equal to delta H1 plus delta H2 plus delta H3. Total enthalpy is always remains constant whether the reaction take place in a single step or several step. This is Hess's law. Okay. So if a reaction proceeds in single step or if a reaction proceeds in several steps, total enthalpy change is always same. Consider these three reactions. Here, carbon is reacting with oxygen to produce carbon dioxide. Here, carbon react with oxygen directly to produce carbon dioxide. Here, carbon react with oxygen directly to produce carbon dioxide. Enthalpy is minus 393.5. Now, consider, let it be 1 and let it be 2. In second reaction, carbon react with oxygen first to form carbon monoxide. So, carbon react with oxygen to form carbon monoxide, and that carbon monoxide again react with oxygen to produce carbon dioxide. Here, the reaction take place in two steps. Here carbon directly react with oxygen to produce carbon dioxide. So reaction proceeds in a single step. Here first carbon react with oxygen to produce carbon monoxide. This is the first step. Then carbon monoxide react with oxygen to produce carbon dioxide. Second step. Okay. Now if you add enthalpies of these two reactions, because here carbon is converted to carbon dioxide in two steps, here in a single step. Now if you add like this. Now if you add enthalpies, if you add these two enthalpies, that is 110.5 plus minus 283.0, you will get 5393. You will get this value minus 393.5, right? That means total enthalpy change is same whether the reaction proceeds in single step or by several steps. Here carbon is converted to carbon dioxide in a single step. Enthalpy change is minus 393.5 kilojoules per mole. Here carbon is converted to carbon dioxide. Here carbon converted to carbon dioxide in two steps. First step, carbon react with oxygen to produce carbon monoxide. That carbon monoxide again react with oxygen to produce carbon dioxide. So here reaction take place in two steps. So when you add reaction, or when you add enthalpy change in these two reaction, you will get minus 393.5, which is similar to this reaction. Okay, this is Hess's law. Total enthalpy change is same whether the reaction take place in single step or by taking number of steps. Total enthalpies always remain constant. Now, what is first law of thermodynamics? First law of thermodynamics states that energy can neither be created nor be destroyed. Enthalpy is a form of energy. Enthalpy is a form of energy. So, enthalpy is a form of energy. Energy can neither be created nor be destroyed. So, enthalpy will be always same. If a reaction take place single step or by taking several steps, enthalpy for a reaction. Enthalpy for a reaction, for a particular reaction, enthalpy will be always same whether it take place in a single step or by taking number of steps. Enthalpy will be same because enthalpy is a form of energy. Energy always remains constant. I think it's clear. This is Hess's law. Moving on to next topic, application of Hess's law. Application of Hess's law. Moving on to next topic, applications of Hess's law. Application of Hess's law. Now first application is calculation of lattice enthalpy. Calculation of lattice enthalpy. Calculation of lattice enthalpy. By using Hess's law, we can calculate lattice enthalpy, delta H lattice. Now what is lattice enthalpy? Okay, lattice enthalpy means it is the enthalpy or energy required to convert 1 mole of solid ionic compound to corresponding gaseous ion. It is the enthalpy change accompany, or it is the energy required. It is the energy required. It is the energy required to break down 1 mole of solid ionic compound. NaCl is an ionic compound. So it is the energy required to break down 1 mole of solid ionic compound to corresponding gaseous ion. It is the energy required to break down 1 mole of solid ionic compound to corresponding gaseous ions. Or it is the energy released. Now when you start from here, we can state like this. It is the energy released when 1 mole of cation in gaseous state and 1 mole of anion in gaseous state react to form 1 mole of solid ionic compound. Okay, if you start from here, you can define lattice enthalpy from solid state or from this gaseous state. You can express or you can define lattice enthalpy from both the sides. Now if you are starting from here, it is the energy required to break down solid ionic compound to corresponding gaseous ions. Oh, now if you define from here, it is the energy released. It is the energy released when 1 mole gaseous cation and 1 mole gaseous anion react to produce 1 mole of solid ionic compound. Okay, this is lattice enthalpy. Now we have discussed nearly 7 or 8 types of enthalpy, like enthalpy of formation, enthalpy of combustion, enthalpy of atomization, enthalpy of fusion, enthalpy of vaporization, enthalpy of sublimation, enthalpy of solution, enthalpy of hydration, bond enthalpy, etc. So we can calculate all enthalpies experimentally, okay, except lattice enthalpy. We can calculate or we can find out values of all the enthalpy for a reaction experimentally except lattice enthalpy. We cannot calculate lattice enthalpy experimentally. Okay, lattice enthalpy value. We cannot calculate lattice enthalpy value experimentally. We can calculate all other enthalpies like enthalpy of formation, combustion, atomization, bond enthalpy, fusion, vaporization, sublimation, enthalpy of solution, hydration. We can calculate all other enthalpies experimentally except lattice enthalpy. So in order to calculate lattice enthalpy, we are going to study, in order to calculate lattice enthalpy, we are going to study Born-Haber cycle. Born-Haber cycle. Born-Haber cycle. Now, Born-Haber cycle by using Hess's law, Born-Haber cycle help us to calculate lattice enthalpy. So, by using Hess's law, Born-Haber cycle help us to calculate enthalpy, lattice enthalpy for a reaction. For example, consider we have to calculate lattice enthalpy of this reaction. Na solid, Cl2 gas react with NaCl solid. So we have to calculate a lattice enthalpy of NaCl solid. Experimentally, we cannot calculate lattice enthalpy. Except lattice enthalpy, we can calculate all other types of enthalpies experimentally. But lattice enthalpies cannot calculate experimentally. Okay. Now consider Na solid react with chlorine gas to produce NaCl solid. Now we have to calculate lattice enthalpy of NaCl. So in order to calculate lattice enthalpy, we are using Born-Haber cycle, and Born-Haber cycle use ideas from, or Born-Haber cycle help us to calculate lattice enthalpy from Hess's law. Okay. So Na solid react with Cl2 gas giving NaCl solid. Now let the enthalpy for this reaction be enthalpy of formation. Here 1 mole of compound is produced from constituent element. So this is enthalpy of formation. 1 mole of compound is formed from constituent element. So this is enthalpy of formation. Okay. Now consider Na solid changes to Na plus gas. Na solid changes to Na plus gas. The enthalpy needed for this conversion is known as enthalpy needed for this conversion. Or first consider Na solid changes to Na gas, not Na plus gas. First consider this one. Na solid changes to Na gas, and energy required for, or enthalpy required for this change is known as sublimation enthalpy. Sublimation enthalpy. Solid to gas, sublimation enthalpy. Now consider Na plus gas changes to Na plus gas. Na gas changes to Na plus gas, and energy or enthalpy required for this conversion is known as ionization enthalpy. First step, Na solid changes to Na plus gas. Energy or enthalpy required for this conversion is known as sublimation enthalpy. Second step, this Na gas changes to Na plus gas. Energy required for that conversion is known as ionization enthalpy. I think it's clear. Now, from here, energy required to convert Cl2 to, now we have to balance this equation. Na solid plus, we need half Cl2. Half Cl2. What is half Cl2? Half Cl2 means it is Cl. So we need only one chlorine. So Na plus half Cl2 giving 1 NaCl. Okay. Now energy required to break down Cl-Cl bond is known as bond enthalpy. Okay. So energy required to convert Cl2. Okay. This is actually half Cl. Okay, but neglecting this half, energy required to convert Cl2 to Cl atoms is known as bond enthalpy. So this is bond enthalpy. But we are considering only half Cl2. We are not considering one Cl2. To convert one Cl2 corresponding Cl atoms, the energy is known as bond enthalpy. But here we are taking only half Cl2, so we need only half bond enthalpy. For one Cl we need bond enthalpy. For half Cl2 we need half bond enthalpy. So energy required to convert half Cl2 to Cl is known as half bond enthalpy. Now next step, Cl is converted to Cl minus gas. Energy required to convert Cl to Cl minus gas is known as electron gain enthalpy. What is electron gain enthalpy? If a neutral atom is gaining electron, for example, if chlorine atom is gaining electron, it will convert it to Cl minus. If a neutral atom, Cl is a neutral atom, if a neutral atom gain electron, then it will convert it to Cl minus. So energy released during this process is known as electron gain enthalpy. When we add electron to chlorine atom, it will convert it to Cl minus. Okay, and energy released when an electron is added to Cl is known as electron gain enthalpy. The energy released when an electron is added to neutral atom is known as electron gain enthalpy. So you will get Cl minus. Now Na plus gas and Cl minus gas, these react to form NaCl solid. And energy required for this conversion is known as lattice enthalpy. What is lattice enthalpy? If you start from here, it is the energy released when 1 mole of cation in gaseous state react with 1 mole of anion in gaseous state to produce 1 mole of solid ionic compound. It is the energy released when 1 mole of gaseous cation react with 1 mole of gaseous anion to produce 1 mole of solid ionic compound. Right? So lattice enthalpy. So Born-Haber cycle is a method used to calculate lattice enthalpy. It is used to calculate lattice enthalpy, and Born-Haber cycle works, or its basic principle of Born-Haber cycle is Hess's law. So I'll start with an example, or I will discuss with an example. Here Na solid react with the half Cl2 gas giving 1 NaCl. That enthalpy is known as enthalpy of formation. Now here the reaction take place in a single step. Let that enthalpy be enthalpy of formation. Okay. Now next, Na solid changes to Na gas. Enthalpy change is known as enthalpy of sublimation. Na plus gas changes to Na gas changes to Na plus gas. That enthalpy is known as ionization enthalpy. What is ionization enthalpy? It is the energy required to remove an electron from outermost shell of an isolated gaseous atom. Or if we want to remove an electron from Na gas and convert to Na plus gas, we have to supply some energy. First we have to remove an electron. For removing an electron, we have to supply some energy. The energy required to remove an electron from isolated gaseous atom is known as ionization energy. So when we supply ionization energy, Na will lose electron to form Na plus gas. Now, energy required to break down covalent bond in diatomic molecule is bond dissociation enthalpy, right? Now here we are considering only half Cl2, so it is half bond dissociation. For 1 Cl2, bond dissociation enthalpy. So for half Cl2, it is half bond dissociation enthalpy. Now we got Cl. Now to convert Cl to Cl minus, we have to supply electron. We have to supply electron. So when the Cl accept one electron, it will convert it to Cl minus, right? It will convert to Cl minus. So energy released when we add electron to Cl is known as electron gain enthalpy. So we got Cl minus. Now Na plus gas plus Cl minus gas gives 1 mole of NaCl solid, that is lattice enthalpy. Okay, I think it's clear till here. Now, according to Hess's law, when a reaction takes place in single step or several step, total enthalpy change is always constant. So reaction take place in a single step or several step. Total enthalpy change is always constant. Here, this reaction take place in single step. So enthalpy of formation. This reaction, Na solid plus half Cl2 giving NaCl solid. This reaction take place in a single step. So enthalpy of formation is equal to, and the same reaction Na solid and half Cl2 react to form NaCl by taking number of steps, right? Okay, here Na and Cl2 directly react to form NaCl in a single step. Now next reaction Na and Cl2 converted to NaCl by taking number of steps. So total enthalpy change is always same. So enthalpy of formation is equal to enthalpy of sublimation plus enthalpy of ionization plus half bond dissociation enthalpy plus electron gain enthalpy plus lattice enthalpy. Okay, now we can calculate all the enthalpies experimentally except lattice enthalpy. So we can calculate enthalpy of formation experimentally, enthalpy of sublimation experimentally, enthalpy of ionization experimentally, enthalpy of bond dissociation experimentally, enthalpy of electron gain experimentally. Except lattice enthalpy, we can calculate all the other enthalpies experimentally. So if we know enthalpies of these, if we know values of these enthalpies, that is enthalpy of formation, sublimation, ionization, bond dissociation, electron gain enthalpy, then we can calculate lattice enthalpy. So lattice enthalpy is equal to, taking all these terms to left side, you will get enthalpy of formation minus enthalpy of formation minus remaining enthalpies. Enthalpy of sublimation plus enthalpy of ionization plus a half bond dissociation enthalpy plus electron gain enthalpy. Okay, so taking all these terms to left side, we can calculate lattice enthalpy. So this is how we calculate lattice enthalpy of any reactions by using Born-Haber cycle. Okay, this is the first application of Hess's law. Okay, this is the first application of Hess's law. I think it's clear.